So we're now recording. Our speaker today is Chris Bruce from the University of Glasgow, and he's going to speak about what you can see on the screen from algebraic actions to sister algebras and back again. Please, Chris, go ahead.
Thank you very much for the introduction and also for the invitation to speak. And additionally for changing the time a little bit to accommodate something else. There was a small error on my part with scheduling, so thank you very much for shifting the seminar a bit. I'm going to speak about joint work with Xin Li, also in Glasgow today, on sister algebras associated with a certain class of algebraic dynamics. So here's the brief overview. I'm going to say what I mean by an algebraic semigroup action, or an algebraic action of a semigroup in this setting. Talk about how to build a sister algebra from such data, and then talk about our approach for understanding the structure of such sister algebras. These have been floating around in various special cases for the last couple of decades. And then I'll talk a little bit about our approaches through the language of groupoid sister algebras, in particular using its so-called tight groupoid of an inverse semigroup, which is something that Rui Excel has developed. There's a very nice general theory that one can apply in this sort of setting. And then I'll explain how to understand these groupoids in terms of the initial algebraic data and what sort of consequences we obtain for the sister algebra, the concrete sister algebra we're interested in. And at the end, I'll go through some more example classes and talk a little bit about rigidity if I have time at the end. Okay, so first, algebraic action. So I'll say what I mean by an algebraic action. For today, we're going to have a left-cancelled monoid S. So it's a semigroup with an identity element. And the action of the semigroup on itself by left multiplication is by injective maps. This is what it means for it to be left-cancellative. The typical example would be a submonoid of a group, right? So you have a subsemigroup of a group that contains the identity element. Then it's both right and left-cancellative even. And an algebraic S action, by definition, is an action of S on a group G by injective endomorphisms. So precisely, I mean, they have a homomorphism, a monoid homomorphism sigma from S into the endomorphisms of a group G, such that each of these endomorphisms is injective. And today I'm going to implicitly assume in many instances that this action is faithful, so sigma is injective, so S is really embedded as a submonoid of the endomorphisms of G. And I also want to assume the action is non-automorphic in the sense that there's at least one element that acts by a proper endomorphism, so something that's not invertible. And the construction I'm going to talk about is sort of degenerate in the case when it's an automorphic action. So there's going to be a groupoid, but the unit space would just be a single point, and there's nothing interesting that comes out of that case. And some of the statements will not be true because of this trivial situation. So I'm going to assume throughout that we have some, in most cases, we have one element that's not invertible. The most interesting setting or class of examples from the point of view of dynamics is when G is abelian. So if the group you're acting on is abelian, you can take the point triagon dual and dualize the action. And you actually get an action of S on the compact dual group in this setting by surjective continuous endomorphisms. And this is really the sort of setup you see in more classically in the dynamics literature. And these have, in this case, when G is abelian and S is actually a group itself, these these algebraic actions have been studied quite a lot in the last several decades, going back to work by Kitchens and Schmidt in the late 80s, even. But they've been studied by lots of other people like Doug Lind and Thomas Ward, to name just a few. But that's just from the motivation to the dynamics point of view. These are really the most interesting when G is abelian, because you really are interested in the dual picture, which is an action on a compact topological space. But then you study them through this the algebraic dual picture. So somehow dealing with the endomorphisms of the discrete group is a bit easier to handle in many situations. But from the point of view of sister algebra theory, the construction and many of the results work just fine dealing with endomorphisms of a general group that doesn't have to be abelian. And it turns out we get examples of exotic groupoid algebras this way. So it's sort of natural to develop things in this more general framework. Okay, so this is what I just mentioned a second ago about examples of groups. When S is actually a group acting on a abelian group, then these have been studied a lot, but these actions of semigroups have been studied much less so in the last few decades. They've received a lot less attention. They do appear in various places, in particular, of course, single transformations, so N actions have been studied a lot. But there's not a well-developed general theory for algebraic semigroup actions of semigroups, which is quite different from the group case. Okay, so I'll mention a couple of concrete example classes here. The first are the full shifts. Of course, there are subshift analogs in the setting as well, but the general setup is we have our monoid S, and we take an alphabet, which we're going to think of, we take a non-trivial group sigma, which we think of as our alphabet. And you can just form the direct sum over the semigroup, where each summand is just a copy of this alphabet. Right? So this is a group. And you have the sort of one-sided shift on the space, which comes from the action of S on itself by left multiplication. And concretely, right, it takes one of these elements, which is the identity outside of some finite set of S, and it translates, if you think of it, it translates left when it can, or it gives you the identity element if you can't translate. So this S inverse T here technically doesn't quite make sense because there's no group around, we can't invert elements in S. But if T happens to be in this ideal of the monoid, there's a unique element, which when you multiply on the left by S, you get T. So that's what I mean by this notation. In the case when S is the natural numbers and sigma's say a finite alphabet, this is the dual of the usual full shift. So this is something, this would just be the finitely the sequences that are eventually the identity element, and then the dual is the dual. When you take the dual, this direct sum becomes a product. So the dual, this would be the sort of standard shift. When it makes sense to take a dual in the abelian case, this would be the sort of standard shift you would see in the study of SFTs and this sort of thing. And another example that's been quite important in the developing the theory of that I'm going to talk about today, and that's really it's one of the examples that I'm very interested in, it comes from ring theory. So in particular, if you take an integral domain, right, so a commutative unital ring with no zero divisors, you can form an action of the multiplicative monoid of this ring on this additive group. So the non-zero elements in this ring form a cancellative monoid because we have an integral domain, and just the left multiplication action of this monoid is by injective group endomorphisms on the additive group of the ring. And this is a class that was first studied by some special cases by Joachim Kunz and Xin Li. I'll come back to this in a few minutes as I go through. These are just two example classes. I focused on concreteness rather than generality. So there are many other classes coming from torial endomorphisms, from commutative algebra, from I mean, really, you can take this. There's quite a lot of different ways of getting constructions from this, even from self-similar groups. There are some constructions, but I'm going to mostly focus on these ones that are related to shifts or rings today. Okay, so each algebraic action, S action as defined above, gives rise to a concrete C-star algebra as follows. So we first we define a representation of the monoid on the Hilbert space L2 of the group. Defined concretely is using this formula here, right? So we take a map kappa, and it takes an element S in the monoid to an isometry that acts on the canonical basis, standard basis vector by applying the endomorphism to the index. So because sigma S is injective for all elements in the monoid, this is actually, there is an isometry that satisfies this formula. So this is something you have to verify. And we use kappa to denote this because we call it the Koopman representation. Technically, in the case when it makes sense to dualize, this is the dual of a Koopman representation, but it's sort of a standard, related to a standard gadget in dynamics. And the C-star algebra you then build from this action is concretely generated by the range of this Koopman representation. So generated by all of these isometries coming from S, together with the reduced group C-star algebra of G. Right, so we're not just taking the range of the Koopman representation, we're taking the isometries and then we're throwing in all the unitaries that come from the left regular representation of the group. So I'm using lambda to denote the usual left regular representation here. And this is a concrete C-star algebra, right? So it contains the reduced C-star algebra of G, but it also contains a bunch of isometries. And the main question I'm going to talk about today is about simplicity, right? So you have this very concrete, you have a concretely defined C-star algebra, and you can ask, when is it simple? Or when is it purely infinite? Things like this. And it's unlike, I mean, there are lots of results on C-star simplicity for groups that say something about when the reduced group C-star algebra sitting inside here is simple. But for this algebra, it's going to be much more important on how the semigroup acts on the group, kind of like cross products, right? So this thing plays some sort of the role roughly analogous to a reduced cross product for the action of S on some dual of G, but there's no dual of G in general. So okay, let me go through a bit of the history of these things. So the C-star algebra, as I mentioned above, was first considered about 2 decades ago by Hirschberg, and sort of a small side project during his time as a PhD student. And he considered just single endomorphisms of amenable groups, actually. And then it was picked up about a decade later, and I think it was 2011, by Kunz and Verschuck, who looked again at single endomorphisms of abelian groups and studied these concrete C-star algebras in that setting. And they came up with a nice K-theory formula, among other things. And there's also some work of Viren here, who considered a slightly more general setting than Kunz and Verschuck and extended things outside of. Kunz and Verschuck had some technical assumptions that were removed in later work. The examples from rings that I mentioned were also studied initially about around 2006 to 2012, roughly. So Joachim Kunz wrote a short proceedings note, and I think it's published in 2008, on examples coming from just the natural numbers, where he defined what's now called the ring C-star algebra of the traditional ring of integers, rational integers. And then that led to work by Xin Li, in a slightly more general setting of C-star algebras from integral domains satisfying some finiteness conditions. And then a bit later in 2010, in Li's thesis, he sort of established a general framework for studying these concrete algebras as with general rings. So I gave a definition for integral domains, but really you can define a concrete algebraic semigroup action and a C-star algebra for any ring, commutative or not. You don't need integral domain, you don't need any of these things. In general, there's some choice about left and right elements or regular elements, things like this, but you have a very general definition. These, I should say, maybe before I go on, this, they were initially interested primarily in examples from number theory, which is something I'll come back to at the end. But then it was sort of natural to understand to what extent you could extend the theory, and I think there's still lots of open, interesting questions in the setting of ring C-star algebras. Actually, there's really a lot we don't know. But I also should point out that one of Joachim Kunz's students, Nikolai Stammeier, did a lot of work on a special class of actions from right LCM monoids. I'm not going to say what they're not going to play a role today, but Stammeier, and then in joint work with others like Brownlow and Larson, wrote several papers. But they were focused more on universal C-star algebras associated with this initial data rather than concrete ones, which is what I'm interested in today. But there's some, nonetheless, they obtained some simplicity results and results on pure infiniteness in special cases when they had amenability in the appropriate sense. And something I did in my thesis and a little bit with Xin Li as well was some examples of special actions coming from number theoretic data. So going back to a couple quick examples of these C-star algebras to get just a rough idea of what they are. So for the usual shift over the natural numbers with an alphabet of n letters, the C-star algebra is just the Kunz algebra ON. So it gives you a concrete representation of the Kunz algebra. This was observed by Kunz and Verschuck. So somehow the easiest example of a full shift, you obtain ON. And this example coming from integral domains, you obtain what's called the reduced ring C-star algebra. So I'm not going to define that, but the definition is exactly what I wrote down if you specialize to the case of the multiplicative action of a monoid of a ring on its additive group. So in general, these sort of algebras have a lot of, we like to say they have a lot of pure infiniteness built in some sense. There's a bunch of relations that automatically appear and happen in these concrete algebras. So unlike semigroup algebras, say you have a concrete Hilbert space, but you actually have a lot of sort of tightness conditions that appear in the concrete representation. So actually you often get simplicity and things like this of this concrete algebra. You don't have to take a quotient by some sort of boundary ideal. And one part of our motivation was to, for the work I'm going to talk about today, was to provide a framework for studying C-star algebras associated with algebraic actions from much more general classes than had been previously studied. So there were examples from rings and these examples from right LCM monoids that were had some intersection, but not too much. But there were lots of other examples, for instance, of certain shifts and subshifts that didn't fit into any of the existing frameworks. And this is one of our motivations, was to try and develop a general theory for understanding these algebras. From algebraic actions that, of course, we want to recover the old results, but also we're really primarily interested in new example classes where the previous techniques just weren't able to say anything. Okay, so the approach is through inverse semigroups. So it's very convenient to use this language of inverse semigroups. You can sort of encode the algebraic action in it as an inverse semigroup, and then you have a whole general theory you can mostly do to re-excel that you can appeal to that allows you to build a nice groupoid, which is our candidate for a groupoid model for this concrete algebra that we're interested in. So I'm not going to say anything about the general theory of inverse semigroups today, but I'm going to write down a concretely defined inverse semigroup of partial bijections on a set. So before I say how to define this, let's recall that by definition, that a partial bijection of this group G, so here G is the group we're acting on, is just a bijective map between two subsets of the group. So we have a map F from so-called the domain of F to the image of F, and it's a bijective map. These are just subsets. You can have the empty function. This is one. Of course, any bijection gives you a partial bijection. These are all fine. And I'll use this IG to denote the collection of all partial bijections. And you have semigroup operations on the set. First, you can compose them. You have to adjust the domains appropriately, and the composition might give you the empty function. If the range of one is not contained in does not intersect the domain of another, you're going to get the empty function when you try to compose these things. But you have a composition, and you also have an inversion, right? You can take a partial bijection and just go back from the image to the domain. So you have a composition and inversion, and this gives you what's called an inverse semigroup. So these formally behave kind of like partial isometries with commuting range projections, if you like. Of isomorphism, they can all be realized that way. But the partial bijections we're going to be interested in today are going to be built from the endomorphic action of the semigroup together with the translation of a group on itself. If you recall, the concrete algebra is defined in terms of these endomorphisms through the so-called Koopman representation, together with the left regular representation of the group. So what I'm writing down now is going to be sort of an algebraic analog to this. So we're going to take the inverse semigroup generated by these endomorphisms, which here we view as partial bijections. Right? So technically, initially these endomorphisms are functions whose domain and codomain is all of the group. But now we're going to just look at the image and view it as a partial bijection from the whole group onto some subset of the group. It might be everything. It might be a proper subset. And this is a partial bijection because we're assuming sigma S is injective for every S in the monoid. And we can also take these translations, which are honest bijections, right? This is just the left translation action of the group on itself, which is by bijective maps. And we take the inverse semigroup generated by these. So you have to take these guys, you take compositions, and you have to take inverses and compositions with the inverses. So it's a bit strange, right? You can invert these endomorphisms in the inverse semigroup of partial bijections. So you get the map that goes back from sigma S of G back to G, that just takes the unique, it's just the inverse. This is an injective map onto it. So it's a bijective map onto its range, and you just take the inverse. In general, these things can be a bit difficult to describe, but I'll come back in a second and sort of tell you what a general element looks like. But I have to introduce a bit of terminology first. But the reason this is relevant and connected to operator algebras is through a sort of a general fact. When you have a inverse semigroup of partial bijections, you can represent it as a semigroup of partial isometries on the L2 space of the set you're acting on. So this is, in this instance, we have a semigroup homomorphism from the partial bijections on G to the partial isometries on this L2 space of the group. Right? And concretely, you take the partial bijection phi, and you send it to this capital lambda phi, which acts on the basis vector delta x. It sends it to delta sub phi x if x happens to be in the domain of your partial bijection, and it kills it otherwise. So because this is a partial bijection, there is such a partial isometry. You have to check, but it's not too difficult. And really, this is the partial isometry whose initial space is L2 of the domain of phi, and whose final space is L2 of the range of phi, or the image of phi, if you like. And we're going to view this as a representation of the specific sub-inverse semigroup generated by the elements coming from our endomorphisms together with the translations. And what you can observe is that if you take an element in the monoid and apply this lambda map to the endomorphism sigma s viewed as a partial bijection, you recover exactly kappa s as before, this Koopman representation. And if you take this representation again and take the translation, this left translation from a group element G, and view it as a partial bijection and apply lambda, you get exactly the left regular representation applied to this element G. So this is the standard unitary. And from this, you can deduce actually that the concrete C-star algebra, this frac A sigma, is equal to the closed linear span of these partial isometries. So we have a representation of this inverse semigroup and the closed linear span of its range is the C-star algebra we're interested in. So this is one step towards understanding this, right? Now we have some collection of partial isometries. It's closed under multiplication, right? It's a nice inverse semigroup. And the algebra we're interested in is a closed linear span of these guys. And from this, you should expect there's some nice relationship between the concrete algebra and the various C-star algebras you can attach to an inverse semigroup. So this again goes back to this general theory of Excel that it builds groupoids and universal C-star algebras. Sorry, the general theory for inverse semigroups is developed by others as well, but we're going to mostly focus on this tight groupoid, which is something from Excel's theory. But there's Patterson and others that have worked on these general C-star algebras associated with inverse semigroups. Okay, so I promised I'd say a little bit about what the elements in this I sigma look like, but to do that, I have to introduce a bit of terminology. So we have these so-called constructible subgroups that are attached to the action. The exact form is not going to be so important later, but I just want to mention it for completeness. The way these are constructed from the group is you take the whole group, you apply an endomorphism from some semigroup element Tm, then you take a pre-image for another inverse for a different endomorphism, and then you apply another endomorphism, take a pre-image, and you do this finally many times, and you get some subgroup of G. Right? It's obtained by applying endomorphisms or applying pre-images. So here, this inverse is a set theoretic pre-image, so it's not quite not the inverse in the partial bijection as above, just a set theoretic pre-image. And these things can be a bit complicated to describe, but all you really know in general is it's some sort of collection of semigroups of G. It turns out it's closed under intersection, which is something that's maybe not obvious, but follows some general theory in the setting. And the reason these are relevant here is the so-called idempotent semilattice of this inverse semigroup we've defined is equal to the cosets for these constructible subgroups together with the empty set. So here, when we have an inverse semigroup of partial bijections, so the idempotents are just the ones that are equal to their own square. But when you have a partial bijection that's equal to its own square, it can just be identified with its domain or range. So it's actually just the identity function on subset of the group in this case. So I'm using notation a little bit in identifying the idempotents with their the corresponding subsets of G. But the point is that this special collection of cosets of G is going to play a very important role in understanding the structure of this concrete algebra. And in fact, it's going to be, we build the groupoid model using this in a minute. But first, now that we have introduced this terminology notation, we have this, we can say exactly what an element in our inverse semigroup looks like in terms of these constructible cosets. And so a general element, if it's not the zero or empty bijection, is going to take some constructible coset GC. Again, we don't really know what these C's look like in general. They're sort of, it's abstract. We know there's this collection of subgroups, but we don't have a concrete handle on them. But it takes this, it removes the G, so it takes you to C. It applies some, now an isomorphism of between two subgroups, C and D, where phi is turns out it's a partial isomorphism of the group generated by a bunch of these elements, endomorphisms and their inverses viewed as partial bijections. And then you translate by a different group element. So somehow this inverse semigroup is encoding certain symmetries, isomorphisms, or certain bijections between constructible cosets of the group. There's a translation, there's some automorphism between two subgroups, and then another translation. And this is the form that these elements take. And in the C-star level, right, we have partial isometries that are just implementing these symmetries. And these are the things that generate our C-star algebra. And the point for us is going to be that this collection of cosets is closed under intersection. So it actually defines a topology on G. Whenever you have a collection of subgroups, it's closed under intersection. It forms a subbase for the topology on G. And roughly speaking, we're going to complete G with respect to this topology. And then there's going to be an action of this inverse semigroup on this compact space we get by partial homeomorphisms. This is the sort of idea for building the groupoid. You can see this all happening inside the C-star algebra in terms of partial isometries, conjugation by partial isometries in some commutative algebra, which we'll see in a second. To get a feeling for what these constructible subgroups look like, we can go to the full shift. If we look at the full shift, again, so sigma is just some alphabet or some non-trivial group. Then the constructible subgroups are just direct sums over certain subsets of S. And these subsets are what are called the constructible right ideals of the semigroup S. And this is something that appeared in Xin Li's general theory of semigroup C-star algebras. I'm not going to say what these look like in general. I mean, they can be very complicated as well, but the point is it connects naturally with something in the theory of semigroup C-star algebras. And in some known examples, people have worked out what these constructible subgroups are. In the example coming from rings, you get what are called the constructible ring theoretic ideals. This is something, again, that appeared in the setting of semigroup C-star algebras. But in nice cases, for instance, for rings of integers, you actually get all of the non-zero ideals in the ring. So I think this is a good idea to have, a good example to have in mind. If you take a ring of integers in a number field, for instance, the usual integers, then the constructible subgroups for the action of the multiplicative monoid are just all of the non-zero ideals in the ring. And this is a particularly nice instance where you can actually compute them explicitly, but this is one of the more important example classes, in my opinion. And the reason it's very convenient to have this inverse semigroup floating around is you have a special set of these idempotents in the inverse semigroup, right? The ones that are equal to their square, they all commute by general principles from the theory of inverse semigroups. And if you take the closed linear span of the partial isometries corresponding to idempotents, then you actually get a commutative subalgebra of this concrete algebra. Here you can actually check that the C-star algebra is precisely the span of the characteristic functions for constructible coset. So why is this? Well, here I'm viewing the characteristic function, right, as an element. First, I view this as an element in L infinity of the group, right? It's a characteristic function of a subset, and then I let it act, view it in the operators in L2. I let it act by multiplication operators as usual. So this is viewed as this is really the multiplication operator for this characteristic function. And the takeaway so far, if you like, is this commutative subalgebra of our concrete C-star algebra that's spanned by a bunch of commuting projections. And these projections, the set of projections is closed under products up to 0 as well. So this is indeed an algebra. And when you have a commutative C-star algebra like this, you can of course look at the Gelfand spectrum. So you take the space of characters in this. This is a commutative unital C-star algebra. So there's a nice compact space. It's general by projection, so we know we're going to have a totally disconnected compact space as its spectrum. And you can describe them completely, explicitly using this. This is what the notion of tightness, that is something Excel has developed in this particular case, boils down to this condition I'm writing down here, where you have these homomorphisms on this semi-lattice of cosets. So they're multiplicative with respect to intersection, 0, 1 valued. And they have this tightness condition that if you have a characteristic function, if it's 1 at some coset, and if you can cover that coset by finitely many other cosets, then this character has to be 1 at one of those pieces as well. So this is a tightness condition that appears. But the point is you can describe the spectrum in terms of the constructible cosets. So it's something described in terms of algebraic things plus this set theoretic condition. And in general, right, the space is a completion of a coset space of G. There's the intersection of all these constructible subgroups, as constructible subgroups of G gives you some subgroup. It might be trivial, it might be, who knows, but it's not going to be normal in general. And you take the coset space for that, and you can check actually that this spectrum, this boundary thing I've written down here, is actually contains this quotient of G as a nice dense subspace. So this compact totally disconnected space that sort of falls out of this construction is really some sort of completion of a quotient of the group we're acting on. I'll give an example in a moment of a concrete description of a concrete example to say what this looks like in a moment.
Chris?
Yeah.
May I ask you a question? I mean, this tightness condition that you describe, I kind of recognize it, but I think that it's not precisely the tightness condition that I have considered. Can you show that they are actually equivalent?
Yes, definitely. So there's some work we had to actually prove in this setting. It turns out that all of the tight representations are the same as the cover to join representations, which is the first step. And then we check that the being a cover to join representation in the appropriate sense is it boils down to this condition I wrote down here. So there's actually a bit of work to check that this is precisely the same tightness condition. So you're absolutely right. This is not just a verbatim translation of the general tightness condition. In this special case, we essentially because this is a very nice property of having, when you have a subgroup that's covered by cosets, this is sort of a very special situation. There's some general theory about what sort of put constraints on how this happens. So it allows us to really describe the general tightness condition in a very special way in this setting. So that's a good question. This doesn't quite look like the general setting. Actually, it's sort of a very it looks like a very special instance of a tightness condition, but it turns out these are the only ones you have in this for this special class of actions.
Okay, thank you.
I'm not sure if this, yeah, but there's some work. There's a little bit of work to check that this is exactly what you get. And I mentioned, so I'm now going to write down this on this totally disconnected space, this spectrum, we have an action of the inverse semigroup by partial homeomorphism. So I'm not going to write down this concretely. It's a bit technical, but you can, when you have this action, you can form the so-called transformation groupoid, which is a certain groupoid of germs. There's a couple different choices for what equivalence relations you take. So I'm using this terminology transformation groupoid rather than the groupoid of germs because it's slightly different than the more classical groupoid of germs. And using general results of Excel here, you can check that there's actually a surjective homomorphism from the full C-star algebra of this groupoid onto our concrete algebra. This follows because this algebra is universal for so-called type representations of the inverse semigroup. I think for this result, I should be assuming S and G are countable. Actually, but I think as stated, at least this requires second countability of this groupoid, but this is a minor point. So this is the connection to our concrete algebra, right? We have this general, we have an inverse semigroup, then we can apply some general theory with a little bit of additional work to get a nice groupoid that we can describe. And just by the general properties of this groupoid that are well understood, we get a map from our groupoid onto this concrete C-star algebra. I mean, this is what I've already said a few times. This is the tight groupoid in the sense of Excel. So it's described. There's a little bit of proof to check that this is the same thing, but it works out. In this case, this is exactly what you get. And as promised, let me give a very simple example to sort of say what this groupoid looks like. If you take one of the easiest actions is if you take an n action, so you take a single endomorphism and just take an endomorphism of the usual ring of integers, just multiplication by 2. Right? This is a fine injective endomorphism. And in this setting, when you can check that the constructible subgroups, this guy here is just the, it's going to be the ranges of powers of the endomorphism. So in general, when you have an n action, so in this case, it's just all of the ideals or subgroups that are generated by a power of 2. And from this, you can check actually that the spectrum of our commutative algebra is just the quadratic integers, which is this inverse limit over all quotients of z mod powers of 2. So this is a very sort of standard space, and the groupoid actually is a partial transformation groupoid. So the group that acts partially on the space is just the semi-direct product where you take the multiplicative group generated by 2. So this notation here, I mean, this is the all powers of integer powers of 2 as a multiplicative group, and it acts just by multiplication on the ring where you just take the integers and then invert 2. So this is the smallest. You're taking this algebraic n action. You're taking a natural extension or a globalization. So you want to dilate this to an action of z, so an invertible action, but then the price you pay is you have to replace z with z adjoin 1/2. So you get something much bigger. And this group acts partially on the 2-adic numbers. It has a nice global action on the 2-adic field, and this is, if you like, is the reduction groupoid to the non-invariant subset of 2-adic numbers.
Is there any peculiarity of the prime 2, or does this hold for every prime p?
No. Yeah, it holds for every prime p. Actually, it even holds for a natural number not equal to plus minus 1, positive natural number. So that's a good point. So I just chose 2 for concreteness, but it doesn't depend on the choice. Yeah, good question. Yeah. And there are lots of versions like this. You can take finitely, it's a bit more complicated to describe, but you can take submonoids generated by finitely many coprime integers, and you get nice examples that have even been studied in some special cases. Actually, the C-star algebra is actually rather complicated, even if you just start taking, if you take more than 2 coprime integers and generate a multiplicative monoid, gives you some free monoid acting, and then that can act just on the integers, or in duality, this is just acting on the circle by some commuting covering maps. And the C-star algebra that this spits out, you have a concrete groupoid model, but it's actually quite, for instance, challenging to compute the K-theory for such things, which is something that people have tried to do a few times. Okay, so I'm going to talk a little bit about some properties of this groupoid. Don't worry, the last slides are a bit shorter, so I have about 15 minutes left. So the algebraic action, we have a notion of exactness in the setting. So we say our action is exact if the intersection of all the constructible subgroups is the trivial subgroup. For instance, this occurs if the intersection of the ranges is trivial, of course, but it's slightly weaker in general. And the reason for this terminology is this is a sort of a vast generalization of something that Rockland introduced in the 60s for single endomorphism. So this is why we use this terminology exactness. In the literature, it's appeared in special cases where, without the language of constructible subgroups, people have considered this intersection condition here, which is also a generalization of Rockland's condition. But in the general setting, you really need to work with something a bit different. It's not very clear why this is relevant, but I'll give the reason this is important in our setting is that the groupoid is actually topologically free if and only if if the action is exact. If the group G is abelian, it actually is an if and only if statement. So in the examples from more dynamical interest, this is equivalent. This characterizes topological freeness. I say topological free here because the groupoids don't have to be Hausdorff actually. So if they happen to be Hausdorff, this is the same as the groupoid being effective or topologically principal for in the second countable setting. But the point is, this is a condition that's quite checkable in many examples that characterizes a very important property of the groupoid. Right? If we want to understand the structure of the groupoid C-star algebra, we need to understand when it's topologically free. And this condition is something that's quite checkable. I'll give an example. Another very nice example, sort of basic example of an endomorphism of an algebraic n action is it comes from an integer matrix that's invertible. So take an integer matrix with that has a non-zero determinant. And then this gives you an action on just the left multiplication by this matrix gives you an action on ZD. The constructible subgroups are just powers, are just the ranges and powers of this matrix applied to ZD. You get these certain lattices inside ZD, if you like. And it's an old result that's known that this is the intersection of these ranges is trivial. Excuse me, if and only if the minimal polynomial of the matrix has no prime factors in this polynomial ring whose constant term is plus minus 1. So we actually have a general result that is specialized to this in a very special setting, but using modules and prime actions and things like this. But this wanted to mention this old result to illustrate what sort of condition this exactness is. So you don't, roughly speaking, you don't want there to be any pieces of the space which you have some factor that acts by invertible elements, right? If you have a factor that has determinant plus minus 1, then somehow it looks, in some sense, it looks like an invertible matrix on part of the space, and that's what you have to exclude. So exactness is saying that there are no subgroups, invariant subgroups on which your semigroup acts by automorphisms. That's really what exactness is. It's saying that even if you find an invariant subgroup and shrink in, that you still act by non-invertible, something non-invertible acts there. So there's no piece on which you restrict to when you get an honest irreversible, or sorry, you'll find no reversible system somehow inside. Imprecisely, this is the condition. The shift sort of is exact if F has a non-invertible element. So it contains non-invertible elements. This is a typo, there should be no BS here. And the example from rings is exact if and only if it's not a field. So this is very mild. These are the two most mild non-degeneracy conditions. So as soon as they're not automorphic, they're actually exact. So in these examples, this is sort of almost automatically satisfied. And we have some conditions that involve Hausdorff and minimality of these groupoids. One of them just comes from general results of Excel and Pardo. The minimality one, we actually have quite a few different minimality conditions, and they take some work. But the point is there are conditions on the action that characterize when this groupoid is Hausdorff or minimal. And they're in principle quite checkable. The Hausdorffness condition is a bit, maybe a bit difficult to work with. The minimality, we have quite a few different ones, and it's actually a bit easier to get a handle on. But for example, if we have an action of finite rank torsion free abelian group is non-automorphic, then it satisfies both of these conditions. And if we take the full shift, then it will be minimal and have this Hausdorff condition as soon as the semigroup is left reversible, which is a fairly weak condition to satisfied, for instance, if the semigroup is abelian, but not in general. And both these conditions, as I mentioned before, are also satisfied immediately if for the example coming from an integral domain as soon as the ring is not a field. So these conditions I mentioned so far are sort of always satisfied, except for some, in the ring setting, they're satisfied except in some trivial cases. The shift is a bit more of a restriction on the semigroup. Of course, for more difficult examples, you have to, these may or may not hold, of course. And it turns out in this setting that we actually get pure infiniteness of our groupoids as soon as you're minimal. So there's this result that if these groupoids are minimal, then they're automatically purely infinite in the sense of Matui. This is not, took a little bit to prove, but it's not so surprising in light of some general phenomenon that people are seeing in the setting of comparison or dynamics and things like this. But it turns out the point is if you have minimality, then you automatically get pure infiniteness. And this is relevant for C-star algebras because of general facts. So this corollary is just that if you have an exact action and if it satisfies this minimality condition, then the so-called essential C-star algebra associated with the groupoid is going to be simple and purely infinite. So this essential algebra, I'm not going to say too much about what it is, and varying levels of generality was introduced by Excel and Pitts, and also in this setting by Konevsky and Meyer. This is a slightly more general setting. It's a quotient of the reduced C-star algebra of the groupoid. It agrees with the reduced algebra when the groupoid is Hausdorff. But in general, it has a better chance of capturing simplicity and pure infiniteness in the non-Hausdorff setting, which is why it's natural for us. And it actually appears in a very natural way in this setting of our work. It's sort of the best. In the exact setting, it gives a nice way of has a nice relation to the concrete algebra if we're interested in. Okay. So now I'm going to go back just and compare briefly with the concrete algebra. We started with a concrete algebra. We built an inverse semigroup, used some general theory to get a groupoid, characterize some properties of the groupoid in terms of the action, and now we're going to go back and try to say how this concrete algebra is related to the groupoid C-star algebra from the groupoid we've built. So this semi-lattice of constructible cosets is a special character that just takes the value 1 at each constructible subgroup and vanishes on all the other cosets for each group. And I'm going to state one special instance of a structural result. The general statements are much more technical. I just wanted to sort of combine a couple of conditions to get a compact statement here. And it turns out if you have an action that's exact, and if this isotropy group is of this special character is amenable, then there's a canonical isomorphism from the essential algebra of the groupoid to this concrete algebra we're interested in. So somewhat surprisingly, I would say, for me, if you have exactness, you actually get a map from the concrete algebra onto the essential one, which is a bit strange. In the setting of things like graphs or left-cancelled small categories or semigroup algebras, you typically have a map from the groupoid algebra, the reduced groupoid algebra, onto the concrete algebra in question. But in this setting, it went the other direction. We often have a map from the concrete algebra onto the groupoid model, which is a bit strange. And more or less is an amenability obstruction to that being injective. In general, it's not quite true, but in most examples, is an amenability obstruction. It's precisely amenability of this special isotropy group. And in nice cases, this isotropy group is just the enveloping group of the acting monoid S, right? And in that case, actually, amenability of the groupoid is equivalent to amenability of this group. So in nice situations, you can really describe this concretely. But I want to mention one slightly different thing that happens is a bit surprising. If you take, we get honest exotic examples in the setting as well. So if you take, for instance, the free monoid on 2 generators, so this F2 plus, and take some non-amenable group sigma, and take the full shift, the full F2 plus shift over sigma, then you actually can check the concrete algebra is sandwiched between the reduced groupoid C-star algebra of our groupoid and the full C-star algebra in such a way that neither of these maps is injective. But the composition here is the identity map on the complex group algebra. So this is what's known as an exotic groupoid C-star algebra. This middle one is really a completion of this complex algebra, but in some exotic norm that sits properly between the full and reduced. And this is a bit of a strange thing. You don't usually run into these exotic algebras arising as concrete C-star algebras, not from. So we were a bit surprised to run into this phenomenon at first. We sort of thought maybe this would always be isomorphic to the reduced, but it turns out this is not the case. And roughly speaking, I don't have much time to talk about this, but there's an immutability obstruction on either side for injectivity. So on this side, more or less, G being amenable, so the group you're acting on being amenable is it's necessary in order for this to be an isomorphism on nice conditions. And this relies on recent results in the theory of induced representations of groupoid algebras by Sergei Neshviev and Johannes Christensen. So this is a bit of work to proving this result. And here is related to this result above, there's a different amenability obstruction in terms of a different isotropy group. And again, you have to use a theory of induced representations for groupoids to work this out. And there's some work to do actually. So the right-hand side is the one where you need these general recent results. And getting a groupoid algebras, the left-hand side is just a bit more concrete calculation. Okay, I have 5 minutes left, so I'm just going to very briefly. Actually, I'm going to skip through. I was going to mention just a couple example classes, but I've mentioned these already a little bit throughout. So I'm going to close with by mentioning rigidity theorem, which is a slightly different slightly different statement, but it's something I think is quite it's been surprising to us initially. So if we take the examples coming from rings of integers, so if you take two number fields with rings of integers OK and OL, then we obtain that the following statements are equivalent. So this is going to very much use these groupoid models. So the first statement is just that the rings are isomorphic as rings, which is equivalent to the number fields being isomorphic. General fact about number fields in rings of integers. Here, the second is that these actions are isomorphic. This again is not too hard. So the equivalence of these two is quite easy, actually. Isomorphic action meaning that I have an isomorphism of additive groups and an isomorphism of the acting monoids that are compatible with the actions. This is sort of the natural thing you would expect. The third statement is that there's an isomorphism of these concrete algebras associated with these two actions that carries the canonical diagonal commutative algebra on the left-hand side to the canonical commutative one on the right. So this is a characterization in terms of C-star algebras. And the fourth condition is that the groupoids are isomorphic as topological groupoids. So the content, it's easy to see that A and B are equivalent, and it's easy to see that either A or B implies C and D. And C and D are equivalent actually by general results in the setting of groupoids and Cartan subalgebras. So this is essentially goes back to a result of Renault, but also this in this special case for partial actions is something that Xin wrote down. So the content in this is going is really D implies A is how we prove this. Essentially, it's going from D to A. So really the content of this theorem, the proof is entirely about groupoids, but it has a consequence in terms of having a C-star algebraic characterization of algebraic number fields, but also a groupoid theoretic characterization of number fields. This is a bit, it's in stark contrast with the result of Xin Li and Wolfgang Luke. They showed in 2012 that these ring C-star algebras, this notation is bad. So this here is the same as A sigma, and this is A tau. That these are always isomorphic independent of K and L. So if you don't keep track of this special commutative subalgebra, this Cartan subalgebra, you have no information. And moreover, you can actually check that the canonical diagonals are always abstractly isomorphic. They're just functions on the Cantor set. So somehow the C-star algebras themselves, the bigger algebras are always isomorphic, and these special Cartan subalgebras are always isomorphic abstractly. But you can have an isomorphism between the bigger algebras that preserves these Cartan subalgebras if and only if the initial data was isomorphic. So you go from having no rigidity to having complete rigidity, depending on whether you keep track of this bit of additional data. And this is what was a bit surprising to us. I think because of this result of Li and Luke showing that these ring C-star algebras were always the same, people sort of forgot about ring C-star algebras for a while, or thought they were not so interesting because there was this sort of huge failure of rigidity for the examples from number theory. So we were quite happy to find that this somehow to keep track of this natural bit of information, or equivalently, if you work with the groupoids, then you really have a complete characterization of number fields in terms of operative algebras or groupoids. And you can, of course, add other equivalences in here. Actually, you can add the topological full groups of these groupoids are isomorphic. So you obtain a class of, and if you look at commutator subgroups, you get these infinite simple groups that are abstract isomorphism class encodes number fields, things like this. There's also some semigroup C-star algebras with AX plus B semigroups that turn out to be isomorphic if and only if these conditions hold. So there's several more statements you can add in here with a bit more work, but for brevity, I didn't include them here. I think I'm just about out of time, so I'm going to stop there. And thank you very much for listening.
Okay, thank you very much for a very nice talk. I suppose the attendance will be boiling with questions. So, see, somehow I don't imagine being quiet, but
I'm just waiting for an opening for me to ask my question. So I mean, I am curious about I mean, first I didn't quite understand, because you're saying that this algebra, this concrete algebra, is in between the full and the reduced groupoid, but at the same time it may be the essential algebra.
So if in the examples where it's equal to the essential algebra, then it's definitely not between them. Then it's on the far right of this diagram. You're absolutely right. So there are some examples where it's isomorphic to the essential, but those are disjoint from the ones where it's exotic. So those
Okay.
classes of action. Yeah. Very good point. So this is when I can go back to this.
I'd like to see the hypothesis again.
Yeah, exactly. So this shift example, for instance, this group is definitely not amenable. Here, this group will be the free group on two elements, this isotropic group. So this hypothesis, and that's the obstruction really to having this map being an isomorphism. And in this special example, actually, the essential algebra is equal to the reduced. So in this diagram, I wrote the reduced because it's the same as the essential for this particular groupoid.
Okay. Now, do you actually have examples in which this gray ideal is non-trivial?
Yeah, good question. So we don't have concrete examples of this. I'm quite convinced they exist, and it's sort of, but I don't have concrete actions where we've worked out to try to describe it or prove. And I think this is a very interesting thing to do. I think this is a natural next step where we had quite a few things, and we decided not to spend as much time on that for the first paper. Just things were just getting too long. We had lots of different questions, but I think this is a very natural question, and I expect we have some examples coming from self-similar groups, for instance, where I'm expect there will be a non-trivial gray ideal, but I haven't verified this. So I have some candidates in mind, and I suspect when we look a bit harder, we'll find more. But this is a very natural question that we have to understand better. And we don't have concrete examples for those yet.
Okay, thank you.
Thanks, Rudy. Yeah.
Are there any questions from the audience?
May I ask a quick
Yes.
related question? So, is this algebra always between the max system algebra of the groupoid and the essential? Do you know this?
So if the action is exact, that's true. Other than that, we don't quite know. But if the action is exact, then it sits between the full and the essential, the max and the essential.
You are not sure.
Yeah, we needed. So we used this this result from Konevsky and Meyer that if you have a topologically free groupoid, then the essential algebra has a certain co-universal property. So you can get a map from the concrete algebra onto it. So we needed this exactness condition for action in order for it to sit between the max groupoid algebra and the essential one. And I think that's a reasonable assumption. It's not the strongest. I mean, it is definitely an assumption. There are lots of examples that are not exact, but it's satisfied for quite a large class of examples. And in that setting, you definitely get that this sits between the max algebra of the groupoid and the essential. And then we have for some special classes of actions, we sort of investigated, we have criteria that ensure that one map is that it's either isomorphic to the essential or that it sits properly between. We have some obstructions on either side that both obstructions and sufficient conditions to get an isomorphism on one side or the other of one of these different maps in the exact setting. I didn't write them out so our paper, we have more complicated descriptions in terms of isotrope and induced representations for there's a certain subgroup of the isotropy group that appears, and there's a quasi-regular representation, and you have to really sort of compare these various representations and then try to use an induction argument. And there's some sort of weak containment. The representations of the groupoids is what you need, and you have to try and understand when you have this weak containment. And we have a bunch of sufficient conditions, but in the most general statement we can say is if we have an exact action, then the max C-star algebra maps onto the concrete one, and the concrete one maps onto the essential.
I guess you said at the beginning that always the max maps onto, right? Or not?
That we always have, actually. That we always have. You're absolutely right. So the max.
The question would be whether this maps onto the essential, right?
Exactly. And we weren't outside of the topologically. The only setting we were able to show this was when the groupoid is topologically free. But it's possible it holds in general. I mean, I'm not sure. We really used this special property of the essential algebra that had this sort of co-universal among algebras that were quotients of the full algebra that for which the map is injective isomorphism on the diagonal. So we use this sort of special property, but it's quite possible that it's true in general. But
I see.
We thought about the sum, and we weren't able to. Didn't see a direct proof. We were mostly interested in the exactness condition is something we needed to say something about this groupoids, the structure of the groupoid C-star algebra, anyways. So outside of that setting, we don't have. We wouldn't be able to say that as much if we had this map anyways, but I think it's an interesting question to try and determine if you always have that.
Mhm.
Yeah, what is the position exactly of the algebra? Okay, thank you.
Yeah, good question. So thanks.
A small question. So, in the situation of the theorem on the screen, was A sigma simply purely infinite?
Yes. So in this setting, actually, so this result was known even back by, I think, Xin Li probably proved this setting. It was known this algebra was simple and purely infinite. It's a UCT-Kirchberg algebra, actually.
Yeah. So it's okay. So yeah, and they're all isomorphic. And now, is there, so in some situations, like graph sister algebras, you can detect there is an invariant, the sign of certain determinant, that tells you whether the isomorphism carries the diagonal to the diagonal. So is there any easy way of detecting whether this condition is met by looking at some invariant, or maybe there is an additional invariant of the sigma and the tau that tells you whether such an isomorphism could exist? I mean, that carries the diagonal to the diagonal.
Yeah, that's a very good question. The short answer is I don't know. That's an excellent question, though. If there's some natural way of, I don't have an obvious candidate in mind, but this is a good idea to look for such a thing. That would be very interesting if you could something related to.
Yeah. Sorry. So if okay, so now that you say that they are Kirchberg algebras, so they are isomorphic because the K theories are isomorphic. So,
exactly. That's
yeah,
exactly.
and
this
so
is how, yeah.
And so from the K theory, so what is the K theory?
Yeah, the K theory is K0 and K1 are both infinitely generated free abelian. So they're roughly speaking, it's the exterior algebra on the free group generated by all prime numbers. It's essentially the description that comes out in the case of the integers. So you get some huge torsion-free. It's just some essentially Z infinity abstractly in both summands. Yeah, it's a bit. So this was first worked out in a very special case by Kunz. In his first note, he has a sort of a sketch of this computation, and then Kunz and Li worked it out for some special cases, and then Li and Wolfgang Luke worked it out in the general setting. And this computation is actually quite hard. It's quite a lengthy K-theory calculation for these, but you end up just getting, essentially it's the exterior algebra on the multiplicative group of the field, but there's some after you throw away torsion. But abstractly, it's just infinitely generated free abelian.
So there is. So I thought that every Kirchberg algebra, at least the unital ones, was isomorphic to a Katsura and Katsura, and this depends on two finite matrices. How can that give such a huge group? I mean, maybe I'm not understanding something. There's
You're right.
Misciting or something.
You're right. All of these Kirchberg algebras do have models like that, and I have not looked into which groupoid would come from this. Which algebra would be the one that gives you this? That's a good question.
I think that there are some conditions for a Kirchberg algebra to be a Katsura algebra, which are probably related to the K theory being finitely generated.
Yeah.
So,
You're right. Yeah. That's the piece I was missing. Yeah. Sure. Yeah.
So maybe you need a slightly more general class of groupoids to exhaust all of the Kirchberg algebras. Okay. Yeah. Yeah, that's a good question though, because I know there are some there are several ways of constructing groupoid models for all of these algebras. It'd be interesting to find which one matches up with these ring Caesar algebras. Actually, this is not something I have thought about, but this would be it's a natural question, or would be natural to do using these. Is it the X? This.
Excel parallel.
Excel parallel was the word. I think these are the ones you need in order to allow infinitely generated K theory. Maybe these Excel parallel groupoids, but I'm not sure off the top of my head.
We have a preprint in the archive where we attempt to deal with infinite matrices, but it's not really in a closed form. Now, I have another question, if I may.
Yeah,
sure.
So you said that this tight spectrum of your inverse semigroup is a completion of G, right?
Yeah, it's a quotient of G. It's some if it's not exact, you have to take this quotient by these intersection of these constructible subgroups.
Okay,
so
but is it a group?
So in general, I don't think it is, or at least it's not in an obvious way. But if the action has a so-called finite index property, so if every one of the endomorphisms, the sigma s's, has finite, if the range has finite index, then actually this spectrum is just the profinite completion of the group with respect to the constructible subgroups. And there, if it happens to be abelian, if these subgroups are normal, for instance, then you will have a group structure. So that's a good question. That's what appeared in that example where we had the two adic integers appearing. That was a natural group structure. And this happens if you have this so-called finite index property, which you happen to have in these number theoretic examples, actually. So here the spectrum is the ring of integral adels, which is a profinite completion of the ring. And this occurs for a fairly large class of actions, the ones that have this finite index condition. It's definitely a strong condition, but there are lots of interesting examples where this does happen. And if the subgroups are normal, for instance, if the G is abelian, then you have a group structure. But in general, it's definitely not clear that it should. I thought about this a little bit, and it didn't seem clear that it does in general. It's more that the group sits in there as a dense, or there's an image of the group that sits in there in a dense way, but it's not at all clear how to define an operation somehow on the. There are lots of characters there that are in the maximal characters of type things that are outside. You don't really. It's not at all clear how to define an operation on these.
Of course, there's a dense set in which you have an operation. So the question would be whether the multiplication is continuous, right?
Yeah, exactly. I guess so. Right. You try to extend by continuity and then check. Yeah, I was looking more initially for something sort of intrinsic using the structure, but this is an interesting question. I mean, we didn't see a structure. We looked at this a little bit, but it's possible there's something there that persists in a greater generality than or outside this finite index abelian setting. Yeah, that's a good question as well.
Okay.
Yeah, thanks.
I don't want to finish this without bragging a bit about it. So this is the paper that has been cited. The AX plus B semigroup by Koopman, right?
Yeah.
So this is the proceedings of the conference I organized in Valladolid, Spain in 2006.
Oh, great. Yeah, this is yeah. It's been a very influential paper in the area. I've sort of grown up working around these semigroup C-star algebras from number theory and things like that, and it really all started with this paper. So it's that's really great. Yeah.
Okay, so if there are no further questions, I will stop the recording.